Hello and welcome back. In this lecture, we're going to talk about the triplet ranking loss. So this is quite similar to the contrastive loss we spoke about a few lectures back, but this time we're working with triplets rather than pairs. So each sample or each input to the network consists of triplets. Here, our triplets are images, but again, your inputs don't really have to be images. They can be any type of input, so they can be matrices or vectors, whatever your application is. So here I'm just going to explain depending on images, but of course this can generalize to any other inputs. So we have three different types of images for each sample. The first image is the reference or anchor image, okay, and the second image is a positive image, which is from the same class as the anchor. And the third image is a negative image, which is from a different class of the anchor. So here, this is the reference image, the anchor image, which is some person. And the positive image is the same exact person, just in a different appearance. And the negative image is just a different person from the anchor person. Okay, so you have the reference image, a positive image, and a negative image. And what you want to do here is minimize the distance between the anchor and the positive image, and maximize the distance between the anchor and the negative image. So this is represented here in this diagram. These two are from the same class, so we want to minimize the distance between them, and these two are from a different class, so we want to maximize the distance between them. So this is the objective of the triplet ranking loss. So again, a sample consists of triplet, example 3 images here in our case, rather than pairs. One image is the reference, which is the anchor image, and we're going to denote this image as IA. And another image is a positive image, and we're going to denote this positive image as IP. And this is similar or from the same class as the anchor image. And the last image is basically the negative image, and we're going to denote it as IN. And this is dissimilar or from a different class from the anchor image. So these three images are fed as a single sample or a single input to the network. We're just repeating what we said previously. So this is the architecture for the network when we're using the triplet loss. So first of all, this is the equation for the loss. And again, you have 3 images per sample. So IA, IP, and IN. And first of all, you're extracting the features of each image using a CNN. Okay, and again, we're using a CNN because our inputs are images. Okay, so we have 3 networks. And one thing to notice is that these networks all share the same weights. Okay, so basically they're the exact same network. These 3 are the same network. We're just feeding them different images. So after we run each image through the network, we have a feature vector. So this feature vector for the for the reference image is FA, for the positive image is FP, and for the negative image is FN. And then based on these 3 features extracted from the CNN, we're going to compute the triplet loss. So we're going to take the maximum between 0 and the distance between the anchor and the positive image, and the distance between the anchor and the negative image. Here we're just going to use the Euclidean distance, but I suppose you can use other distances. It's fine. So our objective is to minimize the distance between the anchor and the positive image, which is FA minus FP, and to maximize the distance between the anchor and the negative image, which is FA minus FN. Okay, so this is the objective. And don't worry about it, we're going to analyze this equation later on in the next slides. And again, we're going to use a margin, just like we did in the previous lecture on contrastive loss and on the hinge loss. So we spoke about the margin, so it's also included here. So basically we take the maximum between 0 and this whole result. This is another representation of the triplet ranking loss I got from this link right here. So again, you have the anchor image or the reference image. You have a positive image, which is from the same class as the anchor image, and you have a negative image, which is from a different class from the anchor image. And you use a CNN. All of them, they're basically the same network. They have shared weights. And you extract feature vectors from each image, and then you calculate the triplet loss. So let's analyze this equation. We have 3 situations. The first situation is when the distance between the anchor and the negative class is bigger than the distance between the anchor and the positive class plus the margin. So in this case, what happens when the distance between the anchor and the negative is bigger? So we have this distance, or this value that we're going to get is bigger than the distance between the anchor and the positive plus m. So therefore, when you're subtracting a bigger value from a smaller one, you'll get a negative value. Okay, that's why we have a negative value here. So then we're going to take the maximum between the 0 and this negative value that we found. And of course, the maximum is 0. So therefore, we have no loss in this case. So this means that the distance of the negative sample is far from the anchor. And this is the most perfect situation we have. Okay, so this is the first situation. And this is basically what we want. Now, let's move to the second situation. When the distance between the anchor and the positive class is bigger than the distance between the anchor and the negative class. So let's analyze this equation. When this value is bigger here, it's bigger than this value. So when the distance between the anchor and the positive is bigger than the distance between the anchor and the negative, then basically when you subtract a smaller number from a bigger one, you'll just get a positive value, right? And again, you're adding your m here. So you have m plus whatever this positive value is. Therefore, you'd get the maximum between 0 and m plus the positive value. So the maximum is, of course, m plus the positive value. That means the loss is greater than m. In this situation, the negative sample is closer to the anchor than the positive one. And this is what we don't want. So this is a very bad situation, and we want to avoid this. Now let's look at the situation where it's in between the perfect situation and the bad situation. So this is the case where the distance between the anchor and the negative sample is in between the distance between the anchor and the positive value and the anchor and the positive value plus m. So in this case, it's basically lying at the margin. So triplets where the negative is not closer to the anchor than the positive, but which still has a positive loss, is basically this situation right here. So in that case, they are at the margin. They're just lying at the margin. So this is okay, but we encourage it to be better. This is why we're including the margin, because we don't really want these samples to be at the margin. We want them to be away from the margin. We want them to be here in this green side right here. So when they're at the margin, then this is okay, but there's still a loss, which is basically m. Okay? So the loss here is m. Again, this is okay, but we encourage it to be better, further from the margin. We want it to be further from the margin. We want these to be here on the green side. So we want them to cross this margin, to cross this orange shaded area. So this is the objective. And that's, again, why we're including the margin. This is where you can visualize the margin thing. So I hope this diagram really visualizes the concept. So our objective is, again, the first situation. And again, you can visualize the concept of confidence right now. Okay, so when the samples are at the margin, then it's not confident enough. But when they're away from the margin, then it's very confident. So again, we want to penalize these correct predictions that are not confident enough, which are basically lying here in the margin area. Okay, now a very important thing to consider is how to choose these triplet images. So how can we choose basically these images? The first thing that comes into your mind is that we should avoid training with easy triplets. So we should, of course, avoid any triplet images that satisfy this equation, because your network will never learn in this case, because the loss is always going to be 0. Okay, so training with easy triplets should be avoided since their resulting loss will always be 0. So therefore, it is crucial on how to choose these triplet images. Now, this is where we're going to talk about hard negatives. So this area is called online triplet mining, okay, or in general, just triplet mining. So when we're speaking about online triplet mining, that means the triplets are defined for each batch during the training. So this results in better training efficiency and performance than offline mining. So offline mining means that we're going to choose these triplets before we start training. But online triplet mining means that these triplets are chosen during training. So let's see how we can choose them. So the negative samples are just called hard negatives. So hard negatives are the negative data points that are the worst within the mini batch. So basically they're just the false positives. What does the false positive mean? It means that points which are predicted as positive, but they're actually negative. So these false positives are called the hard negatives, and the process of selecting them is called hard negative mining. So let me just give you an example. So let's say we're building an object detection system to detect cars. Okay, so our objective is to localize and classify cars in an image. Now what we do is, after training for one or more epochs, then we're going to get the predictions of our model. So you might have correct predictions, which are indicated in this green localization box. So these are the correct predictions, these green bounding boxes. And at the same time, you might also have wrong predictions, which are these red bounding boxes. So these red bounding boxes, we're going to take these wrong predictions and consider these as hard negatives. And what we're going to do is we're going to add these negatives to the training set and retrain. So these are the hard negatives, and this is how we choose these negative samples right here. Okay, so in this case, the network performs better and doesn't predict much false positives. So this is what hard negatives is, and this is how you can include them in your training set. And this is also how you can use them in the triplet ranking loss. That was it. Thank you very much, and I'll see you next time.